Roberts. Paper is presented by Robert Roberts, Richard A. Roberts, Kenneth S.W. Singh, and B.J. S. Parker. The paper will be delivered by Professor Singh.
Thanks, Ron. Where's your iPod there?
This, I think we put it this one.
Okay.
I guess that's okay.
Fine.
You put that in your pocket. Are you using the overhead?
I'm using slides.
Slides, okay.
So, have we got my slides in position? Forward. Yes, here are the names on this paper. Sorry, I have to start by apologising for the fact that I'm here. You've got to listen to me once again. I'd hoped that my co-worker, Dr. Tripasi, would be able to present this paper, but I'm afraid he's back in India again and was not able to travel here for the meeting. What I want to try to do this morning is to tell you a little bit about some results we've been getting on the adsorption of neopentane in particular, by some microporous carbons which we have studied in various ways. We've characterized using nitrogen and argon adsorption in particular. We've been measuring calorimetrically heats of adsorption. We've been calculating entropies of adsorption. And we think we know quite a lot about the mechanisms of micropore filling, at least in a semi-quantitative kind of way. And my purpose this morning really is to make some comparisons as part of the work we're doing, long-term systematic work, in which we're using different types of adsorptive molecules to characterize these highly microporous carbons. So this is the purpose of the paper. It's a kind of preliminary study and part of a long-term project. Now, as you see here, these are nitrogen adsorption isotherms which we've reported elsewhere. And what you see is that these are, broadly speaking, of two groups. We see the ones at the bottom here on the carbo-sieve, the molecular sieve carbon, PVDC carbon, carbo-sieve. This is a commercial form. The other one down here is on one of our charcoal cloths, which has been subjected to a very low degree of burn-off, of activation. The activation in this case has produced, as you see, very fine pores, very little external surface. This isotherm, this plateau here, is virtually flat, so the external surface area is extremely low, and the uptake down here, the affinity of adsorption at low relative pressure, as you see, is very steep. So those two are rather similar. We put those in the same class as highly microporous, giving rise, as I shall show in a moment, to what we call primary why is it doing that?
Just turn it over.
Yeah, mysterious.
You must be right in the right spot.
Yes, and we move.
Okay.
Right. So these two are giving rise to what we're going to call primary micropore filling, which is taking place at very low relative pressure down here. Whereas the other two adsorbents here, featured here, give rise, as you see, to isotherms of completely different character. Clearly, in this case, there is some mesoporosity, as shown by this hysteresis loop in the capillary condensation range of the isotherm. This is another charcoal cloth sample which has been taken to a rather higher degree of activation. And then we have at the top the so-called superactive carbon, which was developed first by Amoco and which is now in commercial production by the Anderson Development Company in Michigan. Now this one has an extremely high nominal BET surface area, something over 3,000 square meters per gram, but of course that's not a real surface area at all, but it gives some idea at least of the tremendous activity of the material. Now all these isotherms, all of them are very steep in this region down here, but it's the part just above that, above a relative pressure of about 0.01, which is different in these two classes, in these two types. Now, this summarizes our view about the ranges involved in the micropore filling processes for nitrogen. And you see here what I said just now about the primary micropore filling, which we believe to be taking place in the relative pressure range up to 0.01. So as Dr. McEnany pointed out just now, this process involving the enhancement in the heat of adsorption through the overlap of the adsorption potentials across from one wall to another across the slit-shaped pores. This only occurs, in our view, at very low relative pressure. It's all a question of configuration and entropies here, integrals here, I'm afraid. But this only takes place at very low relative pressures, and is followed, we believe, by a kind of cooperative micropore filling taking place in the higher range of relative pressure, as you see, but this is still below the capillary condensation part that I'm not talking about today. So these we have characterized and designated as the two mechanisms of micropore filling. We know much more about this one than we know about the other one, but there is now a lot of evidence put together, partly from our experimental studies and partly from computer simulations and theoretical studies, that this one here, this process here, is in fact a reality. So it really does occur when we have an assemblage of molecules filling a rather wider pore. As you see in the case of nitrogen, this would seem to be in the range from about 0.7 nanometers up to 2 nanometers, 2 being the nominal upper limit as given in the IUPAC classification of pore size. Now, what I'm going to do now is to run through the isotherms of nitrogen and neopentane just to see the comparisons of their shapes. And we've done this by plotting in a conventional kind of way for this purpose. We've plotted the amount adsorbed as a liquid volume. This gives a basis for direct comparison. Starting with the superactive material, the AX21, and you see that at the top end here, these two isotherms are coming pretty close together, seeming to indicate that their Gervich volumes are not very different up here. Clearly there is some difference in this region, however, and notice also the small amount of hysteresis here given by the neopentane, not shown at all by the nitrogen. So the neopentane slope is sharpened up here, reasons I'll give later on, and the isotherm also has this little bit of hysteresis. Right, now I'll run through the others quickly. That's for a wide microporous charcoal cloth, this one, and you see an interesting swing over here. Again, the sharpening of the neopentane isotherm in that region, but this time it's the nitrogen isotherm which is showing a little more hysteresis than the neopentane. Right, now we're beginning to see some molecular sieving taking place, but in doing so, we see that in this particular case, the neopentane isotherm is very sharp here and remarkably flat. So it looks as though the pore system, which is operating in the case of nitrogen, is partly within the first range, primary micropore range, filling range here, partly moved up. There is now effectively, because of the more bulky neopentane molecule, has moved right down into the essentially down into this primary micropore filling range. But the isotherm, as you see, is remarkably reversible. Now we're showing up in the next ones some irreversibility, difficulty of penetration of the neopentane at this temperature of 0 degrees centigrade. I should have said these measurements are carried out at ice bath temperature, 0 degrees centigrade. In this particular case, when we do our chromatographic measurements, however, I'm not going to talk about those today, we get a nice distribution, Gaussian type of peak, which shows nice reversibility at a temperature of 150 to 200 degrees. So it's a question of an activation effect here, that the neopentane molecules at this particular temperature can only gain access to a limited amount of the pore structure, and in that case only with some difficulty. I won't talk about the next one, similar sort of effect there. Now, next, and finally we have here two isotherms on material which is clearly mesoporous, a charcoal cloth which we produce through a different way, which is mesoporous to a large extent at least. But you notice, although it's mesoporous to a large extent, there is quite an appreciable difference between the Govich volumes up here at this top end. So the natural supposition here, thinking would indicate, of course, that there's probably the difference up here is probably caused by difference in penetration in the micropore region. We'll see if that would seem to be the correct explanation in a moment. Right, now then, quickly I must run through our alpha S plots. Now we do this, as many of you know, by making comparisons. This is an empirical method of isotherm analysis, which involves the comparison with a non-porous standard. So what we're doing is to plot amount of atoms, but when we back extrapolate these to the adsorption axis, we see that the corrected micropore volumes are clearly quite different. Also, we have a strong indication here that slopes in the multi-layer range are different, and therefore it would seem that the assessment of the external surface area is different in these two cases. And now we run through, that's for the in sequence, the charcoal cloth, again working down in terms of the pore widths. Notice the difference here, that we have a clear break in the curve in this region, which we interpret as showing the difference between the region of primary micropore cutting. This is taking place at an exceedingly low relative pressure, and then running into the secondary cooperative process in that region. And then, of course, by the time we get up to this, at that stage, the micropores have been filled, and then we're building on the external or the mesoporous surface in that region. Right, now we're going down to the narrow pored material, and we see here, again, a clear, very strong enhancement. That means distortion of the isotherms, both isotherms in that region. Fairly flat plateaus, as we would expect. Extrapolate back, very different values of the apparent micropore volumes in those two cases. Similarly there, in that case, and for the carbon serum. Now, this is an interesting one. This is the mesoporous charcoal cloth, the one which I mentioned earlier gave the difference in the Govich volumes at high relative pressure, and I think we can now see why. Because when we extrapolate these back, again, conventional process, we see here, conventional procedure, we see there is a clear difference in this region, which would indicate that the effective micropore volume for nitrogen adsorption is considerably larger, small, but considerably larger than the effective micropore volume for neopentane. In other words, the neopentane is just not getting into the very narrow pores which are available for nitrogen adsorption. But now let's see how all this comes out when we carry out the analysis of those alpha S plots and see what sort of comparisons we get using our conventional procedure to analyze the external surface areas and the micropore volumes. These are BET values, first columns in both cases. Those are the sort of fingerprinted values, but of course we're not able to attach any physical significance to those, as I said earlier. External areas are here, calculated from the slopes of the upper regions, the multilayer regions of the alpha spots. And then we have the extrapolated values to the intercept on the uptake axis to give us the apparent pore volumes. Now what we're seeing effectively here, I think, is that there is, on the whole, there is remarkably little agreement between these corresponding values. If you notice here, external area with respect to nitrogen appears to be 230 square meters per gram, as against an external area with respect to neopentane, 130. Again, large difference in this one, 218, 132. Almost by chance, I think we get quite good agreement in this particular case, 19 and 22, that's remarkably good agreement, but those are very low external areas in any case. This particular case, as I mentioned earlier, this one is much more significant, I think, because here we have got, I think, a reasonable correction of the micropore contribution, micropore filling contribution in the case of the nitrogen adsorption. And when we make the correction, the corrected value of the surface areas, that is the surface area of the non-micropore part of the material, is in quite reasonable agreement. So those values, I think, are probably meaningful to some extent. So, as a result of all this, I think what we have to conclude is that we must place emphasis on the mechanisms of micropore filling rather than trying to define the limits of micropore size in a kind of an absolute way. This is the conclusion that we draw at this stage, and we believe that what is causing the difference here is in fact the fact that we have a micropore size distribution in every one of these solids, and that we're picking up not only various degrees of penetration, differences in degrees of penetration between nitrogen and the more bulky neopentane molecule. Neopentane molecule has a diameter of around 6 angstroms, of course. We're picking up clearly differences in penetration, as we can see from the molecular sieve effects, but there is a more subtle influence than that. And the more subtle thing, we think, is that as one replaces nitrogen by neopentane, for a set of pores in the intermediate range, the primary micropore filling process can extend for neopentane in the wider range of pores than it can for nitrogen. So we're picking up differences which are affecting the shapes of the isotherms, moving across this critical range from the primary micropore filling into the secondary micropore filling. That is around relative pressures of 0.01 to 0.02. Thank you very much.
Thank you very much. That is open for questions. Yes.
What was the material that you used to determine your non-porous reference isotope?
We used a number of carbon blacks, ungraphitized carbon blacks, and also some material which we call sooty silica, which is being produced by the deposition of carbon layer on the surface of silica. So we have a coherent layer, strong coherent layer of carbon produced by a polymerization process on the surface of the non-porous silica and aerosol type of silica. And in fact, the reduced isotherms, the standard isotherms, come into remarkably close agreement with a range of carbon blacks, things like Elf-Tex. And we have to be careful with the carbon blacks, of course, because some of them are microporous to a limited extent. So one has to proceed carefully, step by step. But the fact that we have the evidence showing that we're not relying on just one supposedly non-porous standard, that gives us more confidence, of course, in the interpretation.
Yeah, well, I'd like to refer to that very high surface area carbon that you had, so-called surface area. We know what you mean high absorptive capacity. And the fact that the neopentane apparently gave a higher surface area and tended to enlarge absorptive capacity as well.
Yeah.
What kind of structure have you in mind that would accommodate such a behaviour pattern? Because it's very difficult to think of a behaviour pattern that would give this kind of absorption. I've been playing around with this for quite a while.
Well, I think that in that material, it seems to me from the, we've done a lot of work on the adsorptive properties. We've not ourselves studied this by electron microscopy in the way that we have for the, in the case of the charcoal cloth samples. We know a lot about those, and as Brian McInerney said earlier, most of those are made up by to a great extent, slit-shaped pore structures. So we're not as confident in talking about this highly active material, but I think probably in that case the pores are of two types. I think we do have a certain proportion of the slits where the localized graphitic structure is merging together in the way that McInerney described. So where we see the graphitic layers coming together, then we have these slit-shaped pores. But I think in addition to those, the wider pores probably have a completely different type of shape. And I think these are much more open, probably because of the way that the material has been produced in the first place through this very drastic chemical process, of course, which has taken place, the KOH treatment, the hydrothermal treatment involving strong KOH, which is an extremely drastic chemical process. And that seems to have disrupted the whole system, produce some exfoliation and opening up of the whole thing. In our in our charcoal cloth samples, as in the molecular sieve type carbons, PVDC carbons, we believe that the pore structure is fairly closely related to the molecular structure itself. So there is a link between them. You're actually, I think, etching out the molecular structure, which in our case, of course, is derived from the cellulose, regenerated cellulose. And that's how one arrives at these remarkably uniform slits. Why, in fact, you can, in the course of activation, the burn-off, you can widen the slits in a regular fashion. Now, clearly with the other material, it doesn't happen like that at all.
Two more questions.
The fact that you get higher pore volume with the large neopentane than nitrogen was very interesting. Are you suggesting this is because the pores, the dimensions of the pores are getting comparable to that of the neopentane, maybe 2, 3, 4 times as big, then you get more cooperative effect?
Yes, I think it depends, that's right. I think it depends on the mechanism of the pore filling process which applies to that particular system. And that means the given solid, microporous solid, and the particular probe molecule that you're using. And so one has to define, I believe, the mechanism in relation to that system. I think this is the point, and that's where we're trying to focus attention, rather than, as I say, trying to define these limits. It seems to me a rather waste of time to maybe some people have been trying to do, is to define whether the upper limit of the microporous should be 20 angstroms, 15 angstroms, and so on. I don't see that gets one very far to do that.
Brian.
Yes, I'm just trying to comment on that last point. The enhanced adsorption, the primary filling that you described, in model pore calculations, that enhanced adsorption is a function of the absolute width and the diameter of the absorption.
And the polarizability.
Yes. So it's reasonable that the pore range over which enhanced absorption occurs should be larger for a large molecule. So I'm sure you're right there.
Exactly.
The other point I want to comment on is your evidence for the transition from primary filling to cooperative filling from alpha plots. You showed a break in the alpha plot.
In one case.
One case.
Yeah.
Now, if that is representative of the transition from primary filling to cooperative filling, then you should see a clearer break in a finer core carbon in that one, and no break perhaps in a wide core carbon. So my question is, have you explored the occurrence of this break as a function of what you know about the pore structure?
It's a good question, and we have done that. If you remember our Hilton Head paper, we did go into that in that particular point in much more detail. And you're right, there is a difference. Where the carbon is, where the micropores are giving rise predominantly to the primary filling process, one doesn't see that break at all. You just see the clear, very pronounced distortion of the isotherm. Where, however, the pores are straddling the range, then you stand a very good chance of picking up this break, as we've done in a number of cases now. The problem about this is that you really have to map out the isothermal pores on the reference material, non-porous reference material, in very great detail, and have a fair amount of confidence in that, to explore this region. That's vital to do it. So one has to proceed carefully, but we have a lot of examples where we show that break. So we do believe it's genuine.
One last question from Glenn Scott.
Is it known whether this AX21 material loses area on heating? And do you know whether there are any unusual dimensional changes when absorption takes place?
That's a good question. I suspect that there are some dimensional changes taking place, but I haven't evidence. Maybe Dr. Dollimore does. On the heat treatment, we've only heated this material up to temperatures, outgassing up to about 400 degrees centigrade. It certainly doesn't change up to that temperature. Of course, it would change if you had any residual oxygen left in it, because it's going to be extremely active, very active material. So you have to be careful when you're dealing with it. But it doesn't change up to that temperature, and I'm not sure. David, do you know about that?
Well, as supplied, it comes with about 30% water.
Yes.
And so far, studies have been concerned simply with driving off the water.
Yes.
And following what's happening when we do that. The danger when you've driven off all the water is it simply has a remarkable tendency to catch fire.
Very good.
Yeah. But it is, nevertheless, the properties are quite reproducible. No doubt about that.
Yeah, fully.
It's good.
Thank you very much.
Thanks.
Fourth paper this morning.